In Florida, there's a special lab studying lightning. ABC's Bill Blakemore went to pay a visit.
At any one moment, there are about 2,000 electrical storms on our planet. It's a constantly crackling ball of lightning, about 100 volts a second, striking people, houses, power lines, airplanes.
Normal commercial plane about twice a year.
A given plane.
Yeah.
Electrical engineer Martin Newman is in league with Jove himself. His 100-acre lab in Florida is plugged into the biggest source of electricity there is. This is the only full-service lightning study center. One experiment here, how to protect planes. They rarely crash when they're hit, but their navigation systems can get knocked out by a lightning bolt's current.
We can map the whole electric and magnetic field that a plane would be bathed in. Everything's attached.
Newman pulls thunderbolts down from the sky by firing rockets, each trailing a wire as high as the Empire State Building. The wire attracts lightning from miles up that follows it back to the ground.
Starting countdown. 5, 4, 3, 2, 1, fire. Lightning!
High-speed cameras capture each microsecond, revealing not just one stroke, but a second, then a third and fourth, and a rare glimpse of a beta defect that's still a mystery to science. But they did measure the electricity right next to the lightning bolt, vital data for redesigning airplane wiring for bad weather.
There's some storms in the Midwest that produce nearly 100 lightnings a second.
Newman's experiments have already helped to protect runway lights from lightning. He's also hitting power lines with lightning, learning to protect them. And he's built this house, which he's hitting with lightning, to discover ways to make your wiring safer.
That's one of the intents, is to make sure that we can have a safe house. That you can sit in here and watch TV while we strike it with lightning.
Right. But don't try this on your house. It's better to leave these experiments
Fire.
to the experts. Bill Blakemore, ABC News, at the University of Florida's Lightning Center.
All right, lightning!
Near Gainesville.
Okay, so we got a bunch of questions that we need to answer. Number one is, what's lightning? Light in lightning, where does it come from? How about the heat? How about the sound?
In Florida, there's a...
One of the things that we will focus on is the fact that whenever the lightning is happening, there are many questions regarding lightning. Number one, number two, number three, number four. Is it originating from the ground or is it originating from the clouds? I hear that people just go, oh, it's coming from the clouds. Some people claim, I mean, it's seemingly it's coming from the clouds, but there are people who will claim that it's coming from the ground. Notice that the airplane just got struck by lightning.
It's one of the very early strikes that we had where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in the canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the electrical field inside the cloud.
Each and every single airplane, I'm talking about the commercial airplanes, they get struck by lightning at least twice per year. As long as you're on the inside, you're perfectly safe. So the question is why? A couple of answers that you could come up with, and a lot of people say, well, because the outside is metal, happens to be a good conductor. And then you got plenty of insulating material between you and the metal of the airplane. Some people will also say, oh, you know what, the airplane is grounded, whatever that means, or it's not grounded, whatever that means. So my question becomes, so what would happen if you were to just get rid of the insulating material between you and the metal of the airplane? Imagine that you're touching the inside of the metal with both hands. Would you get shocked? All right, a lot of you guys will say yes to that. A lot of you guys will say, oh yeah, of course you're going to get shocked, because, you know, the metal is good at conducting electricity. You're touching the metal. And if you touch the metal from inside, of course you're going to get shocked. Despite the fact that the answer is no, absolutely not. You'll be perfectly fine. How's that possible? Well, you'll find out. It's a beautiful picture, like the smile on her face. High ground versus the low ground, which one is more likely to be struck by lightning? Swear National Park. I was there last year or the year before. I was working full time at the community college there nearby on a temporary full-time assignment, so that was fun. College of Squares. All right, so her brother thought that it was funny that her hair was rising up just like that. And then so snapped a picture. And shortly after they left, the lightning struck. I think one person died, a number of people got injured. All right, so I would give yourself 5 points for the question. Of course it is. So the question is, she's on a mountaintop. So high ground versus the low ground, which one is more likely to be struck by lightning? You know the answer, right? So it's going to be high ground. So the question is why? If high ground is more likely to be struck by lightning, and the answer that most of you guys will come up with is because the distance is shorter between the clouds and the ground. The gap is smaller, the distance is shorter. That's distance is smaller, not shorter. All right, so the question is, if that logic is so correct, why is it that the tallest structure in every single city, in my case it's Chicago, is not the one that's getting struck by lightning 100% of the time? All right, so Chicago's famous Sears Tower is in the background, and the distance between this building and that building is less than a mile. All right, so this is where my school used to be, and this is less than a mile. Notice that the lightning strikes a small building as opposed to the taller one. So the distance between clouds and the tallest structure is going to be smaller, yet the lightning is missing the tallest structure. So how's that possible? Thought this was going to be an automatic. Click, click, click. All right, so the charged Coulomb is attracting water. So the question is why? And a lot of the answers that I'm getting is, people say static electricity. Guys, that's just a title. You could have said physics, you could have said science, you could have said, oh, this is not poetry. You're not answering the question. Question is, how's this happen? Static electricity is just naming a title is not the same as answering a question. So you just identify the title of the lecture in essence. Here's the sort of answer that I get. So Coulomb is charged. And then if Coulomb is positive charged, the water is negatively charged. If the Coulomb is negatively charged, the water is positively charged. So that's the sort of answer that I get. So they're opposite charged. Are they really?
Jerry Stiller is mad.
Man, I'm going crazy.
He bought this plastic wrap to keep his fruit salad fresh.
Only I can't get it from here to the food.
Jerry, you should have bought Glad Cling Wrap. Glad unrolls smooth and easy and clings tight when you need it to.
Comes out easy.
Yep.
And clings tight.
Absolutely.
Hello, Glad
Oh, no,
Cling Wrap.
Jerry, don't get mad. Get Glad. Glad Cling Wrap.
All right, so cling wrap, or plastic wraps in general, will cling just fine to glass, porcelain, not so much to things made up of metal. Why are they so clinging when it comes to glass and porcelain, and they don't cling well to metal pots, for example? All right, so everything is going to be related to this lecture. This lecture is on static electricity, or the way we say it, electrostatics. And this guy has something to do with it, with the way everything is shaped in physics. You'll recognize him. You'll recognize him because you'll see his picture on a $100 bill. This guy is Ben Franklin. So the question is, what's his contribution, which made him worthy of having his picture on a $100 bill? It's kind of odd because you would think that everyone would know the answer to this question. Surprisingly, not too many people do. All right, number one, he, unlike the other pictures that you see on different dollar bills, this guy was never the president of the United States. And you see Washington's picture on a dollar bill and a $100 bill. People decided that Franklin's picture is worthy of a $100 bill. So he must have had a contribution somehow to the success of the United States that made him worthy of having his picture on a $100 bill. So the question is what? Some of you guys just mistakenly think, hey, he flew a kite in an electrical storm. Did he really? Let's presume that he did. So who cares? So he made a few scientific contributions. He was considered to be one of the best physicists of his generation. He was considered to be one of the best physicists, once again, who ever lived in the science history. But none of them is going to make him worthy of having his picture on a $100. We don't do that. We don't care much for scientists today. We never did 100 years ago, 200 years ago, or 300 years ago. It's the United States culturally different from the rest of the world. All right, the esteeming people because of their contributions to science, arts, or whatever. That's a European thing. That's not an American thing. If you're Kardashians, yeah, people will recognize it. If it's a commercial, if it's commercial arts, movies, blah blah blah. If it's sports related, entertainment related, yeah, you will have a certain amount of fame. But if you win a Nobel Prize in physics, for example, no one cares. It's a big deal outside of the United States, kind of like soccer is. If you win a Nobel Prize, for example, if I were to win a Nobel Prize in physics, it would be a big deal in Turkey. I would be recognized forever. They would name streets after me. They would school streets. Possibly they would put your picture on their currency. But aside from that, in the United States, no one cares. This is not something which is highly valued in the United States. So we have his picture on the dollar bill, not because of his scientific contributions, but because of something else. So the question is, what did he do for the United States that made him worthy of having his picture on a $100 bill? I don't know why people get really confused when there's a question like that, because you guys know something about Franklin. Some people go, oh, he invented the eyeglasses. Okay, maybe he did. So that's not going to make him worthy of a $100 bill. So that's not going to happen. Some people say, oh, here's the reason why we got the, daytime savings. All right, so the clocks move backward and forward depending upon the season. Well, yeah, he's the guy behind it, but once again, that's not going to make him worthy of a $100 bill. He's got hundreds of contributions, very small contributions, and they don't add up to anything for the most part. All right, they don't really add up to anything. The question becomes the difference between Canada and the United States. Guys, in the United States, we have 50 states. They combine into a one single state of the United States of America. There's a federal government here. And notice that Canada is not included in it. So what's the difference between Canada and the United States? A lot of you guys don't realize that there's a distinct differences between Canada and the United States. Number one, it's a separate country. And they decided to remain loyal to Britain, and the United States decided to separate from Britain. That's the difference. And big part of the decision because of this guy's ideology. He thought that the United States would be better off, the colonies would be better off on their own. He pushed for that ideology, in essence. All right, so you will find them behind the scenes of the Declaration of Independence. In fact, this is the guy who pushed for it. And then you will find them behind the scenes of Constitution. He was one of the main editors of the Constitution. This is the guy who went to France as an ambassador from colonies. And then he convinced France to join the colonies against Britain. Without the French help, there was a lot of financial help from France, as well as military aid from France. France ended up sending troops. There is no way the colonies were going to be able to gain their independence. This is the guy who negotiated that. This guy was the diplomat's diplomat, in essence. Part of the reason why he was accepted in France, he was able to gain access to the king and his court, was because of his background. All right, this guy was a philosopher, political philosophy. He was pushing for the ideals of democracy. And then he was a well-known physicist, natural philosopher. All right, those are the two things culturally that Europeans appreciated. This guy was as famous as a rock star by the time he went to France. So he had full access to the court. He had full access to the king. Eventually, Washington started to win small battles here and there. And then France decided that it's probably it was a risk worth taking to be on the side of the colonies. They end up spending a lot of money so that the colonies would actually win this war of independence. Once they did, somebody had to sit down with British to get him to sign the independence, the documents related to independence. Guess who did? Who was behind that? This guy literally sat down with British and negotiated the independence. Hence the reason why you will see his picture on $100. All right, so this guy is the difference between the United States and Canada. This guy is the difference. And the reason why he was able to gain all that access was because he was also considered to be one of the best physicists of his generation. So what's his contribution to physics?
Franklin's curious mind now becomes intrigued by one of the great scientific mysteries of the 18th century, the phenomenon of electricity.
Never in my life has anything so totally engrossed me. While I was making experiments and then repeating them for my friends and acquaintances who come in crowds to see them, I don't have a moment for anything else.
In Franklin's day, electricity was much more of a puzzle than gravity had been a century earlier in Newton's time. Everybody was familiar with things falling and all. But electricity, it was just a matter of rubbing something and getting some sparks. Where did this come from? Very mysterious.
For Franklin, the pursuit of electricity started as a game. There was an itinerant Englishman who went from town to town showing gadgets that produced scintillas and sparks and could do things.
In one popular demonstration, a group of people hold hands and then receive a collective shock from an electrostatic generator. This game is performed by people around the world.
With the kind of mind and the curiosity he had, Franklin wanted to go beyond the amusement.
The great thing about every one of these parlor tricks and simple phenomena of attraction, repulsion was why. Before Franklin, no one had any clue.
Franklin puzzles over electricity for almost 10 years. Why is a stream of water attracted to a charged glass rod? Can you kill an animal with an electric shock?
How about a person? There was a puzzle in Franklin's time they knew that you can charge things up through rubbing. All right, so you could get a rod and rub it up against an animal fur. In fact, get two of them, rub them against animal fur, and then they would just repel. And then get one of the rods and just rub it with silk and give it a try. All right, so the question is, charged objects will repel or attract each other. So what's causing the attraction and what's causing the repulsion? Franklin was able to explain that. He said, just suppose, he said, there are two types of charges. But there are two types of charges, he said. Let's suppose that the like charges will repel, non-like charges will attract each other. All right, so...
At the time, everyone assumed that electricity was some mysterious force created by rubbing two different substances together. Through experimentation, Franklin proves that in fact, the friction does not create electricity, it simply moves a charge from one body to another. When these charged bodies are brought close together, the result is a spark. Electricity flowing through the air.
This theory was based on the concept of an electric fluid, like an electric current, and that this could exist in bodies in a surplus or a deficiency. He called one state plus or positive and the other minus or negative.
Before Franklin, people had no idea what electricity was or how it worked. After Franklin's fundamental insight, the phenomenon of electricity could be understood and harnessed as a force to change the world.
Okay, so charged objects will either attract or repel each other. Franklin said, if you assume that there are two kinds of charges, you can explain the attraction as well as the repulsion phenomenon. They said that the like charges will repel, the unlike charges will attract each other. That's it. Okay, at the time of Franklin, they thought that the electricity was an electrical fluid, and then the fluid would flow from a state of excess to the state of deficiency. So the excess state was called positive state, the deficient state was called the negative state. That's the reason why it calls one state the positive, the other state the negative. Today, we know that these charges are particles. You will find these particles inside atoms. The center of the atom is going to occupy the positive charge, and the negative charge or charges will move about the center. They will move about the center. They will just revolve about the center. So modern theory, when I say modern theory, I mean the modern theory is the 21st century physics. Early modern theory, let's go with the early modern theory, 20th century physics. The atoms was assumed to look like the planetary systems. Positive charge would occupy the center, just like the sun does in the solar system. And the negative charge or charges will move about the center, just like the way the planets do, relative to the sun. All right, so the positive charge at the center is a proton. Negative charge or the negative charges moving about the center, those are the electrons. Lowercase e represents the unit charge. There are two unit charges, positive and negative. Once again, the positive is proton, the negative is electron. The unit charges have an experimental number, which happens to be very small. You got 18 zeros before you get the first number. Believe it or not, the value of a unit charge was first measured here in Chicago, about 15 miles from here, at the University of Chicago, in 1907. And the guy who measured it ended up winning the Nobel Prize in 1922 in physics. All right, so net charge, things could be charged positive or negative. Remember the Coulomb attracting water? That Coulomb was, for example, it was negatively charged. All right, so net charge means the sum total of all charges. So you're summing up all the charges, positive or negative. In this case, I'm looking at, we got 4 negative charges, so the net charge is given negative 4 E. All right, so here's a formula that we use. Q represents the net charge. N is going to represent the total number of charges that you have. Lowercase e represents the unit charge. In this case, we got 4 negative unit charges. I'm adding 1 positive charge to it. Now we got 3 negative charges. Now we got 2. Now we got 0. Net charge is going to be 0. So when the net charge is 0, call it neutral. So it's got 0 net charge, so which means it's going to be neutral. Now I got 5 positive charges, 4 negative charges. Net charge is going to be positive 1. So now this becomes positive charge. Originally, this was negative charge. Now it is positive charge. When it's got equal number of positive and negative charges, it's known, it's said to be neutral. All right, so pick out the best answer and put your answer on the side. Okay, very good. The same number of protons as electrons. Very good. You guys got it. All right, give yourself 5 points on that one. Conservation of charge simply means that the charges, positive or negative, the unit charges, they cannot be destroyed or created for that matter. So you cannot create these charges, you cannot destroy these charges, which means that the total charge in the universe is going to remain constant. That's what it means. The total charge in the universe is never constant. For example, the electron is the smallest negative unit charge that you can have. You cannot take an electron and break it into something smaller than itself. All right, so this is known as the conservation of charge. So given the fact that you cannot create or destroy charges, how do you make something positive or negatively charged? All right, so let's go back to the comb, which was attracting water. That comb was negatively charged. How do we charge something up positively or negatively, given the fact that you cannot create or destroy charges? Well, you cannot create or destroy charges, that's a fact, but you can move charges around, right? Number one, the charges will reside within atoms, and the atoms usually have equal number of positive and negative charges, but you can strip charges from atoms. All right, so you can free charges from atoms. You can strip charges from atoms. So this process of stripping charges from atoms is known as ionization. Or process of liberating charges from atoms is known as ionization. So there are 3 ways you could do that. Number one is friction. That's the most obvious way of doing it. Number 2 is heat. Number 2 is heat. Let me just explain something in a way that you can relate to. For example, I do drink coffee most of the time because I don't get too much sleep, 5-6 hours a night usually. Wakes me up. Some people are not coffee drinkers. I feel sorry for those kind of people because how do you go through life without caffeine? I don't get it. But if you wanted to, though, you can energize yourself. If you really are feeling tired, and if you need a bit of a boost of energy, give yourself 2 points. Miserably is great, man. Just boil the water. Don't put coffee in it. All right. Here's a cheaper solution to your problem. Just make sure that the water is like 100 to 205 degrees, right? Just put your hand in it. Just soak it in. Just keep it there for like 15 seconds. That's going to wake you up. You will feel energized. You're going to bounce all over the place. For days, you won't be able to sleep. Right? Guess what? Electrons feel the same way. When you hit them up, they're going to be bouncing all over the place. They will be so energized that they're going to end up bouncing out of the atoms. So that's what happens. Remember, we discussed heat. Heat is energy that flows from hot to cold. And when the particles are energized, they're moving faster. So that's what happens. So you energize these electrons, and they're just going to bounce out of the atom. Okay, so that's another way you can actually liberate electrons from atoms. The third way is kind of surprising. This comes out of modern physics. It's the light. Certain frequency of light can energize electrons out of atoms. Okay, so they will liberate themselves. They will have enough energy to escape from atoms. All right, so ionization is a process of liberating electrons from atoms. So electrons are the only ones you can free from atoms. And then friction is one way of doing it. You can heat up the atoms, obviously, so that's another way of doing it. And the third way of doing it is light. All right, so what little we covered so far, let's apply this to the lightning phenomenon. So what's lightning in essence? That was a question that I asked before. Let's start answering the question. So lightning is an electrical discharge. Okay, it's opposite of ionization. In the ionization process, you're literally separating the electron from the atom. During lightning, what's happening is electrons and the atoms are coming together. And when that happens, tremendous amount of energy is being released in the form of light, sound, as well as heat. So lightning is opposite of ionization. It's called electrical discharge, in essence. Lightning is an electrical discharge. So the question is, what's causing the initial separation of the charges before they come back together again? So is it the friction, is it the heat, or is it the light? All right, so the lightning phenomenon is related to the clouds. All right, and then clouds are made up of cotton, you might think, if you're about 3. All right, and then what happens inside the clouds is responsible for the lightning phenomenon. All right, so lightning is, not the lightning, the clouds is composed of water vapor, in essence. That's what you got. So it's composed of water, in essence. And so something happens within the clouds, it causes the initial separation of the charges. Positive charges rise to the top, the negative charges will sink to the bottom. All of a sudden, you got this clear separation of the charges. So the first question is, what's causing the initial separation of the charges? So how do we liberate these electrons from atoms? What's going on? Well, there are 3 cases that you can look at. Either the charges become separated because of friction. So the question is, friction among what? Something should be rubbing up against each other. What's going on inside the clouds that requires any sort of rubbing? You could say heat is responsible for it, but the next question is, wait a minute, heat, what do you mean heat? up where the clouds are, it's usually not that hot. It happens to be fairly cold. In fact, the lightning clouds tend to be at altitudes where the temperature is usually a freezing temperature. It's about 32 degrees or less. So heat is obviously not responsible for the initial separation of the charges. We can say it's light, but the question is, light from what? Seriously, you're thinking, it's light from the sun. Really? So the lightning doesn't happen at night? It does. So are you thinking, it's probably light from the stars? I don't think so, guys. Moon? Absolutely not. So, which means that the light is not the reason for the initial separation of the charges. Heat obviously is not, because inside the clouds, those are freezing temperatures. Where they are for the water molecules. And all of a sudden you're thinking, wait a minute, it's 32 degrees or less at that altitude. So what happens to water at that temperature? Well, it freezes. So you got these, the condensed water, the steam is going to keep condensing, and obviously it's going to form ice crystals at that temperature. And it's going to be windy inside, so there's going to be a lot of friction among ice crystals, ice particles. So the friction among ice particles will be responsible for the initial separation of the charges. And then something weird happens. What happens is the negative charges sink to the bottom, the positive charges go up top. So the initial separation of the charges is caused by friction, and now we got this further separation of the charges. As a result, the top becomes positive charge, the bottom becomes negative charge. So what's causing the further separation of the charges? Okay, and a lot of people, once again, mistakenly think that, hey, wait a minute, look, the ground is positive charge. That's the reason why the bottom of the clouds will be negatively charged, the top of the clouds will become positively charged. The reality of it is the ground is actually negatively charged initially, only after the initial separation of the charges inside the clouds, and only after the further separation of the charges, when the bottom of the clouds become negatively charged and the top of the clouds become positively charged, the ground is forced to become positively charged. So the separation of the charges inside the clouds will cause ground to become positively charged. So this is an after effect of what takes place inside the cloud. To this day, we have no idea what causes the further separation of the charges. We don't know why the top becomes positive charge. We don't know why the bottom of the clouds become negative charge. There's a question mark here. This is a lingering question that we don't know how to answer over a century. What that means is in physics, we don't know everything. It's just not math. For everything that we know, there's a billion things that we don't. All right, the science is a process of gathering information through scientific method, guys. For everything that we know, we have rough answers, good answers sometimes, but we don't know everything. And this is one of those things that still remains a mystery. Top of the clouds will become positive charge, bottom of the clouds will become negatively charged after or further separation of charges. How that happens is still a question of research and investigation. And then after the complete separation of charges, the ground is going to become positive charge. How? That's something that we will discuss.
Although lighting can reach temperatures exceeding 50,000 degrees Fahrenheit, these superheated bolts are actually created by ice. Inside clouds, air currents carry water droplets to higher, colder altitudes. As the droplets rise, they freeze into ice crystals. These crystals join to form hailstones. The heavier hailstones drop through the cloud, colliding with more of the smaller rising ice crystals. During these collisions, electrons break free from the ice crystals and bond with the hailstones. The rising ice crystals create a positive charge at the top of the cloud, while the falling hailstones create a negative charge at the bottom. Eventually, nature neutralizes the opposing charges. Essentially, lightning is a spark, not unlike the spark created by shuffling across the carpet and touching a doorknob. Except this spark can be 90 miles long and carry a charge of more than 300,000 amps of current. In contrast, the electric chair uses only 5 amps to take a human life.
All right, so the initial ionization, the charge separation in lightning is caused by the friction among ice particles, right? So that's as far as we got. We don't know what causes the further separation of the charges. All right, so separating charges, the ionization process. This is from a chemistry perspective. It's a little bit more accessible approaching this portion of physics from a chemistry perspective. All right, so the atoms are neutral, which means that they will have equal number of positive and negative charges. You're looking at a sodium atom. 11 positive charges, 11 negative charges, so this is neutral. All right, if I were to remove a negative charge from it, the electron, now it's got 11 positive charges, 10 negative charges, so it's going to be positive charge. This is known as a positive ion. It's got an excess positive charge. All right, so A is the best answer, so give yourselves 5 points for that one. Here's a fluorine atom. It's got non-positive and negative charges, so it's neutral. If I were to place one more electron here, so it's going to have 10 negative charges and non-positive charges, so it becomes negatively charged. It's known as that negative ion. All right, so far so good. Give yourselves one. All right, so C is the best answer for that. Give yourself 5 points. I'm just going to make everyone. All right, so moving forward. All right, guys, the best answer is A, right? The charges are separated by the friction among ice particles. All right, so A is the best answer. One person got it right. It's the friction among ice particles. Okay, so once you liberate these charges, I'm talking about electrons, there's a way you can move them around. So there are materials which are really good at conducting these electrons, transferring electrons from one point to the next point. These are known as conductors. Anything which is metallic is a good conductor, obviously. The prime examples, metals, living things like you and I, are also good conductors. And there are things which are not so good at conducting these charges. Those are known as insulators. You've got rubber, glass, cork, plastic, paper. All right, these are not real, or wood. These are not good at conducting charges. So the question is, what causes certain materials to be really conductive and certain materials to be very, very much insulators? It's related to something called the Octet Rule. So for those of you guys who are taking chemistry, will probably remember this. Octet means 8. It's known as the 8th rule, the Octet Rule. It's an interpretation that chemists kind of came up with. We don't usually use that sort of interpretation in physics. Physics is a lot more sophisticated. And applied quantum theory to modern physics becomes chemistry, and chemists have ways of making sense out of the information that they get from physicists, so they call it the Octet Rule. So it's the 8th rule. So the 8th rule is, or Octet Rule, is related to the outermost shell. All right, so these are shells: inner shell, middle shell, the outermost shell that you're looking at. This is known as the valence shell. All right, so regarding the valence shell, each and every single atom will have a desire to complete their outermost shells, the valence shells, up to 8 electrons. So which means that they will get into chemical reactions in order to satisfy the octet. So they will either grab or lose electrons in order to satisfy the octet. For example, this is a sodium atom. In order to satisfy the octet rule, it can grab 7 electrons from somewhere else, or it can just lose the one it's got. Okay, so which one is easier? Obviously, it's easier to lose the one it's got now that the octet rule is satisfied. So the sodium atom is going to have a tendency to become positively charged. You got a fluorine atom. Only thing it needs to do is just to grab 1 electron from somewhere else to satisfy the Octet rule. So which means that it's going to have a tendency to become negatively charged. So the Octet rule kind of explains how the conduction takes place. So you got 2 metal atoms. All right, so both of them filled with the outermost shells have 4 electrons. So this needs 4 more. So it's this one. So what they will do is they will do electron sharing. So the electrons will jump from one atom to the next atom. These are known as conduction electrons. So the electrons are free to move within the structure. All right, so the Octet rule is not satisfied. As a result, electrons are shared among the atoms. So that explains what happened. Insulators, on the other hand, their atomic structures are such that the Octet rule is satisfied, in that their outermost electrons, their outermost shells, already filled up with 8 electrons. So if you just go in there like plastic, guys, this is your Disneyland. This is not plastic. What you're looking at is a noble gas in reality. All right. I just decided to give you kind of a quick conceptual version of what an insulator does. So just imagine that this is the comb that we were looking at. So through friction, you start depositing electrons onto this. Notice that the electrons have no way of attaching themselves to any of the atoms. As a result, the comb becomes negative charge. So that's what the insulators do.
On an insulator, an electric charge stays where it is. But on a metal, it spreads out instantly. That is, the metal conducts electricity. On a deeper level, this is what happens. Each atom of a metal can be thought of as a positive ion with 1 or 2 loosely bound outer electrons. When 2 metallic atoms are very close together, the outermost electrons can pass easily from one to the next. As more atoms are added, electrons can range farther afield. Those mobile electrons are known as conduction electrons, and they give metals their special properties. In this way, all metals are electric conductors because every metal is like a giant molecule in which a number of electrons are shared equally by all the atoms. Picture it as a structure of positively charged ions, glued together by a fluid of mobile electrons. But on a metal, it spreads out instantly. That is, the metal conducts electricity. On a deeper level, this is what happens. Each atom of a metal can be thought of as a positive ion.
So the conduction electrons will get shared. All right, so this needs an electron, this needs an electron. So what they're doing is they're sharing the one single electron among themselves. All right, so that's what happens with the conductors. This is the reason why the electrons are free to move within the conductor. Pick out the last answer. Okay, so A is the best answer, so you guys got that. Using a piece of paper, the only thing we have to do is just charge up the comb once again through friction, and then bring it near a neutral paper.
Hold the comb near the paper.
And all of a sudden you realize that the neutral paper is interested in the comb. Why? Because it feels attracted to it. How is that possible? This piece of paper is neutral. The only thing we know is the like charges will repel, non-like charges will attract. Well, why is it a charged object attracts a neutral object? The reason is because within the structure, charges are free to move inside the atoms, guys. Charges are free to move inside the atoms. All right. So you got a negatively charged object. You bring it near a neutral surface, and the surface is made up of atoms. Within atoms, you got equal number of positive and negative charges. So what's going to happen to the negative charges within atoms? They will be repelled into the surface, further into the surface. What's going to happen to positive charges? They will be pulled towards the surface. So what happens? The surface will become polarized, which means that surface is going to become positive charge. Net charge is still 0. Don't get me wrong. This plastic is still neutral, except the positive charges are pulled to the surface. The negative charges are repelled deep into the surface. As a result, the surface becomes positive charge. So this plastic will become attracted to the negative charge rod here. This is known as polarization. So the neutral surfaces can become polarized if you bring a charged object nearby. The charged object will repel the like charges into the surface and pull the unlike charges to the surface, polarizing the surface. While it's neutral, it's going to have equal number of positive and negative charges. The balloon, through friction, rubbing through friction, or friction through rubbing, more like it, is negatively charged. So the wall becomes polarized. Plastic wrap by design is polarized. It's uniformly polarized. All right, so the surface is negatively charged. The positive charges are pushed inward into the structure. Glass is an insulator. It's neutral. Glass becomes polarized. So if plastic is negatively charged, the surface of the glass becomes positively charged. You got the attraction. Plastic wrap is not going to work on metal pods because the metal is a conductor. It's going to take the negative charges from plastic and transfer those charges to the ground. As a result, the plastic is going to lose its charge and it's not going to cling at all to metal or anything else. All right, so pick out the best answer. All right, so the best answer for this one is polarization. Polarization is the best answer. Okay, very good. You guys got that one. Those of you guys who picked C, absolutely. That's awesome. C is the best answer. Those of you guys who picked D, all right, kind of got the concept a little bit reversed. But C is the best answer. Okay, you may have seen this before. It's known as an electroscope. This is known as a gold leaf electroscope. The leaf is going to be gold usually. You got this metal piece. It's neutral. It's got equal number of positive and negative charges. If you bring a negatively charged rod, notice that the positive charges are pulled to the surface, the negative charges repelled. As a result, the rod becomes polarized. Okay, so if you bring a negative or positive charge, the opposite charge will be pulled to the surface. So this is polarization phenomenon. Now, if you touch the rod, the negative charge rod, to this metal top, metal is like a conductor. So what's going to do is it's just going to grab these negative charges from this insulator, and these negative charges will get distributed all over the rod. So the rod becomes negatively charged. This is known as charging by contact. So you can charge these metals positive or negative by touching them. So the charge is, if your body is charged, for example, if you touch a doorknob, the charges will move from you to the doorknob. The doorknob is going to become positive and negative charge depending upon the charge that you're holding. All right, so notice that this is original negative charge. If it touches the metal on top, the metal becomes negative charge. Right? So electroscope is originally neutral. So if you touch it with a positive charge rod, it's going to become positive charge. You transfer the charge to the metal. So the best answer is that. I don't think anyone got it. All right, so you can charge something up by contact. Also, you can charge something up through induction. It goes like this. So you got this metal sphere. It's on an insulated stand, so it's not touching the ground. So you bring a negative charge rod nearby. Surface becomes polarized. So this side is positive charge. Opposite charge is negative charge. Opposite side is negative charge. And then you get a grounding wire. Grounding wire is a wire that touches the ground. That's what it means. So within the wire, the charges are free to move. So what's going to happen is these negative charges inside the rod will repel the negative charges inside the sphere, metal sphere, into the ground, because the furthest the negative charge can get is the ground, away from a negative charge ground, while the positive charges are being held in place at the surface. And then when you get rid of the grounding wire, this is positive charge. It's called charging by induction. Right? Charging by induction or polarization, it means the same thing. Once again, you polarize the metal sphere first by bringing a charge object nearby. All right. Charge object is going to hold the opposite charges on the near surface. The like charges will get repelled into the ground through the grounding wire. And as soon as you get rid of the grounding wire, the net charge is going to be the opposite of the charge of the ground. All right, so what do we have on this one? Okay, so we're going to negatively charge rod right near one end of an uncharged metal bar. The end of the metal bar farthest away from the charge rod will be the same charge. So it's going to be negative, right? So C is the best answer. Most of you guys got that right. Give yourself 5 points. Okay, so we got a sphere carrying a positive charge. So we got 2 spheres. One of them is A, the other one is B. The B is going to be neutral. So we end up placing near each other on an insulated table. So sphere B is briefly touched with a wire that's grounded. All right, so B is going to be briefly touched with a wire to the ground. So which statement is correct? Okay, let's take a look at it. So sphere A is positive charge. So if sphere B is briefly grounded, positive charges will leak into the ground, so it's going to become negatively charged once you remove the ground. So A is the best answer. All right, so those of you guys who got A, give yourselves 5 points.
We all know that like charges repel and unlike charges attract. But can we produce an attraction between a charged object and one which is uncharged? Let's see what happens when we charge this lucite rod by rubbing it with this cloth, bringing it near some paper on the table. The paper can't wait to jump to the plastic. What happened here is that the charges in the paper...
One of the things that I want you to realize is, not that you didn't notice it before, you're able to cause this attraction or repulsion without any contact, obviously. So that's charging by induction is that process. Okay. Something weird about it though. Look, the comb is negative charge, right? The paper is neutral, meaning that the paper has equal number of positive and negative charges. You know that the like charges will repel, the unlike charges will attract each other. So we get that. But why would a neutral paper be attracted to your comb if that's the case? because there's going to be a force of attraction between the positive charges and the cone. I get that. There's also going to be a force of repulsion between the negative charges and negative charges in paper, right? So shouldn't the force of attraction cancel out the force of repulsion? Okay, so the answer to that question, it should, but it's not happening. All right, because the amount of attraction between the positive charges and the cone and the amount of attraction between negative charges and the cone are not the same. Why not? I mean, the cone is neutral, it's got the same amount of positive and negative charges. So why is it that the attractive force is larger than the repulsive force? Why is it that the force of attraction is slightly larger than the force of repulsion? All right, the guy who was able to answer that question was this guy. His name is Coulomb. All right, kind of looks like Washington. This is probably the fashion of the day. This guy is a Frenchman, French physicist. Charles Coulomb is the guy who was able to answer it. He said the reason why the force of repulsion and attraction don't cancel each other is because notice that positive charges after the polarization process are actually closer to the negative charge cone. So the separation distance between the charges will matter. So closer the charges are, the larger the force is, further away the charges, the smaller the force is. So the distance between the charges will matter in terms of the magnitude or the strength of the force. So Coulomb came up with an expression that looks like this. This is known as the Coulomb's law. Okay, something about this expression is worthy of discussion. So Q represents net charge, net positive or negative charge, or two net positive charges. Net charge is the total number of charges that you have to remember. So the force is going to be directly proportional to the product of the net charges, product of net charge or net charges. It's going to diminish inversely with distance is the square of the distance. And there's also an expression here, K, which is going to give you the strength of the electrostatic force. Okay, you have seen an expression like that before, but we were discussing gravity. All right, so Coulomb's law is identical to Newton's law of gravity. All right, so let me just go over this so that you guys make the connection. So the gravitational force is going to be proportional to the product of the masses. Okay, so which means that you multiply the masses. This force is going to diminish with distance, measured relative to the center of mass of the masses, squared. So it's going to be inversely related to the square of the distance between the masses. So further apart the masses are, the smaller the force is. Closer the masses are, the stronger the force is. And capital G represents the strength of gravity. Remember, this is a small number. You got like 10 zeros before you hit the first number. So that makes gravity extremely, extremely weak. Coulomb, in essence, did the same thing. He says, okay, well, he says, this electrostatic force is going to be directly proportional to the product of the masses, no product of the charges, net charges, Q1 and Q2 are net charges. It's going to be inversely related to the square of the distance between the charges. And the electrostatic force is going to have a strength. The strength of the electrostatic force is fairly large. This one is 1 billion. And this is 10 to the minus 11. This is almost like a trillionth. All right, and that's it. That's what he came up with. All right, so the question is, why do these formulas look the same? The answer to that question is because Coulomb did something which we consider today as plagiarism. Okay, if I were to do that, I would definitely destroy my reputation. Not to mention, if you're a researcher, you may end up losing your job. If you guys were to do that, they would probably flunk you first, and then if you repeat it, they may kick you out of school. All right, so it's plagiarism is you're taking somebody else's work and redoing it without giving any credit to the original source. That's what it means. So he's just, this guy ended up coming along about a generation after Newton that he grabs Newton's work, plagiarizes it, and then comes up with this equation without giving him any credit. So the work is kind of stolen from someone else. The only reason why we know that is these are known as inverse square laws. If he wanted to do it from scratch, he probably would have come up with the same exact formula, minus the square part. Okay, this square part requires that you know calculus. And the only reason why Newton was able to come up with it because he was inventing calculus when he was solving this problem. And no such luck with Coulomb. All right, Newton is like Michael Jordan of physics, and Coulomb is one of those NBA players. Okay, it's not in the same league. All right. And there's a reason why he wouldn't give credit. That part of it is nationalism. Brits and French never liked each other. Case in point, the War of Independence for the colonies. All right. So, and here's the reason why. There's no way you can come up with a square. This is not something you can pull out of your butt. Everything else is an assumption. This requires a justification, and no one else in history had the justification that Newton did, because Newton was one of the inventors of calculus. Aside from that, the formulas look the same, and they have the same interpretation. All right, so what else do we have? Space permittivity constant requires a little bit of massaging here. All right, so this is the strength of the electrostatic force that could be expressed in terms of a different constant, which is known as space permittivity constant, which means that the electrostatic force does not travel in space at an infinite speed. This is going to put the brakes on in terms of how fast the electrostatic force can travel from point A to point B. That's what it means. So the formulas look the same. All right, so the idea the formula is stolen, plagiarized, despite what Coulomb claimed, but there are distinct differences between the nature of these forces. Gravity is weak, extremely weak. Electrostatic force is extremely, extremely strong. Gravity is only attractive. Electrostatic force can be attractive as well as repulsive. So these are the differences between the forces. So the next question becomes, how does this force get transmitted through space without any physical contact between the charges? Newton faced the same question about a generation earlier. All right, so when he claimed that the force of gravity extended all the way out to the moon and beyond, natural philosophers of Europe, I'm a little bit exaggerating, it's the French as well as the German physicists, thought that it was nuts. They were not convinced that Newton was right at all. They thought that Newton was incorrect, and they thought that Newton didn't know what he was talking about. They respected Newton as far as mathematics was concerned. They figured that he was a genius mathematician. Physicist, not so much. What was the problem? The problem is the following. Something about force. All right, now take a look at this. I want to show you something which bugged the hell out of everyone. All right, let me just pull this out so you can see a small demo. All right, so Newton's first law, object at rest will remain at rest. Object in motion is going to remain in motion in the absence of an external force. So what happens when there's an external force? External force overcomes that inertia. It causes acceleration, right? Apply a force on something, it goes from rest to motion. It starts to accelerate in the direction of the net external force. Cool. Now, notice that I transmitted the force through contact. Okay, so I'm just going to repeat the same thing without touching it. I'm going to push on it without touching it, nothing happens. I'm going to pull on it without touching it, nothing happens. So what's the condition for transferring force? Physical contact. So in the absence of a physical contact, can you transfer a force? The obvious answer is no. Okay, for me to be able to transfer a force, there has to be physical contact. So notice that there's no physical contact between the moon and the Earth. Right? So how does the force of gravity, through a complete vacuum of space, all through a distance of 250,000 miles, extend all the way out to the moon without any physical contact and influence the motion of the moon? How does that happen? Newton, being a genius that he was, came up with the best answer. His answer was, I don't know, and I have no idea. He didn't quite say it that way. He said, I think no hypothesis. He said, I don't know, I think no hypothesis, meaning that I don't even have a theory regarding how that happens. He said, it simply does. That's it. Gravity extends all the way out to the moon, and it simply does. Then his laws of motion and the mathematics and the observations backing up in mathematics prove that Newton was correct. That's it. He came up with a theory. The theory made predictions, numeric predictions, testable predictions. Those predictions were tested through observations. And then guess what? The gravity extends all the way out to the moon. How it does so? He said, I have no idea. He said, I'm going to leave that up to the future generations to figure that out. All right, so the next generation of physicists came up with the force field idea. We know that the force can be transmitted through space in the form of force fields. Gravity extends all the way out to the moon and beyond in the form of a gravitational force field. And the electrostatic force does the same thing. Okay, I mean, you're able to attract a piece of paper without touching it using a charged comb. You guys have seen it. So which means that the physical contact is not required, which implies that there's a force field between the comb and the piece of paper. All right, so we have an understanding. You can turn on and off your TV by using a remote control. You could do the same thing. You can lock and unlock your car by using a remote key. So that's how it happens. We have a pretty good understanding that this sort of stuff is possible, that you can transfer a force through space in the form of a force field. So the idea is how, given the fact that we got positive and negative charges. Okay, so physicists decided to come up with, I don't want to use this, it's a boring word. They decided that the force field is going to be generated or emitted by positive charges. So positive charges are emitters, transporters, and the negative charges will be receivers. So they came up with these models, visual models. Positive charges become the transmitters, the negative charges become the receivers. It's almost like this is a transmitting station. This could be the radio station, and this could be your radio. All right, so you got the radio receiver here. You got the radio station here. So transmitter, receiver, transmitter, receiver. Positive charges are the transmitters. The negative charges are the receivers. Positive charges will transmit the force. The negative charges will receive the force. All right, so the positive charges will emit the electrostatic force field, which is known as electric field. E represents the electric field. The negative charges will receive the electric field. Once again, E represents the electric field. So the basic concepts. All right, so positive and negative charge. Positive charge is the emitter, the negative charge is the receiver. Every single electric field line emitted by the positive charge will be received by the negative charge, so they will be attracted to each other. And electric charges will repel. And here's the reason why, based upon that visual representation. So the positive electric field lines will always start on a positive charge, and they will always be directed away towards a negative charge. All right, so that positive charge, and you got a negative charge. Notice that the positive charge is 3 times larger than the negative charge. So which means that 1/3 of the electric field lines created by the positive charge will end up on a negative charge. Okay, so the next question is, how does the force get transmitted? How does the force get transmitted? This one is Q, this one is Q. All right, so positive charge, okay, positive charge creates the electric field. And this electric field created by this charge is going to go onto the other positive charge, and it's going to act on the other positive charge. So by acting on the next charge, which is the second charge, it's going to induce a force on it. All right, so the electric field acting on the second charge is going to induce a force on it. So the electric field acting on the charge is going to induce a force on it. The electric field acting on this charge is going to induce a force on it. So that's how the electric field gets transferred. So the electric field, electrostatic force field, acting on the charge will induce a force on it. So this is how the electric field gets.
To Faraday, the 1/r² force between electric charges suggested that the force must be applied by something radiating outward from charges. Something which, like light from the sun, never stops and never ends in space. As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path. These lines of force would begin only on positive charges and end only on negative ones. And they would flow smoothly through space, never crossing or angling. No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together, and weak far from the charges where the lines are farther apart. The ability to apply a force resides at each point in space, and the force arises from the intensity of lines, regardless of the location of the charges that create them.
Okay, so let's create a region of 2 opposite charges. One region is positive charge, the other region is negative charge. Notice that there's going to be a uniform electric field pointing from the positive charge region to the negative charge region. And then let's just drop charges into this region. Let's check to see what happens. All right, so that setup is known as a parallel plate capacitor. It's a capacitor, which means it's a charge holding device. So one region is positive charge, the other region is negative charge. One place is positive charge, the other place is negative charge. I'm going to drop a positive charge, I'm going to drop a negative charge, and then I'll place a neutral atom there. So the electric field acting on the positive charge will induce a force on it in this direction, in the direction of the electric field. As a result, what happens is positive charge is going to accelerate in the direction of the electric field. Electric field acting on the negative charge will experience a force in the opposite direction of the electric field. So the positive charge is going to accelerate in the direction of the electric field, the negative charge is going to accelerate in the opposite direction of the electric field. So positive charges will move in the direction of the electric field, the negative charges will move in the opposite direction of the electric field. Positive charges will accelerate in the direction of the electric field, the negative charges will accelerate in the opposite direction of the electric field. If I were to place a neutral atom right here, all right, so notice that this section is positive charge. There is no opposite charge here, this section is free. So it's the same as bringing a positive charge rod near a neutral atom. What do you expect? The electric field is going to polarize the atom. So the negative charge is going to get pulled in this direction. Positive charge is going to get pushed in the opposite direction. So the atom is going to become polarized. Now that the atom is polarized, what's going to happen? The negative charge is closer to the positive charge region. So the force of attraction is going to be larger than the force of repulsion. So this thing is going to become polarized, and then it's going to start to move towards the source of the electric field. So that's what happened. All right, so let's do a summary of the summary of the summary of the summary. Okay, so positive charge experiences the force in the direction of the electric field, therefore accelerates in the direction of the electric field. Negative charge will experience the force in the opposite direction of the electric field, therefore it's going to accelerate in the opposite direction of the electric field. The neutral atom will become polarized, and it is going to move towards the source of the charge. That's it. It becomes polarized and starts to move towards the source of the charge. All right, so here's a neutral atom inside the electric field. So negative charge is going to experience the force in the opposite direction of the electric field. So it's going to move in the opposite direction. Positive charge will experience the force in the direction of the electric field, so it's going to move forward. As a result, the atom will become polarized. All right, so I think for the next portion of the discussion, it's important to know that the charges are uniformly distributed. That's what it means, because it's metal. All right, so this plate is metal. If it's metal, the charges will be uniformly distributed. Notice that, look at the spacing between the charges. It's equidistance between the charges. Like charges will repel each other, and then the furthest that they could get away is going to be the surface. Once they hit the surface, they will keep moving until they're equidistances from each other. So the charge distribution is uniform. As a result, the strength of the electric field is going to be constant within this region. Why is that important? It'll become important when it comes to the lightning phenomenon.
Both give off light of the same color and have a crooked direction. Lightning and this discharge both give off a noise like a crack, and both are conducted by metals. The electricity generated in the laboratory is attracted to a pointed metal rod. Since they are similar in every other way, will lightning too be attracted to an iron rod? Let the experiment be made.
In the previous century, Newton drew a connection between the motion of the moon and a falling apple. In his century, a century later, Franklin drew the connection between sparks in his laboratory and lightning bolts in the sky.
Franklin hits on a method to prove experimentally that lightning and the sparks in his laboratory are exactly the same. They only differ in scale. The events of this fateful day are described by his close friend and fellow scientist, Joseph Priestley.
Secretly, because he was afraid of being made fun of, and with only his son as a witness, he raised a kite into an oncoming storm. Fixed upon it there was a pointed wire, which was to draw the lightning from the clouds. They were in the storm for a considerable amount of time with nothing happening. Then, just as he was about to give up, he put his knuckle to the key and felt a definite electric spark. Can you imagine his excitement? The exquisite pleasure of that moment. He transferred the charge from the key to the electric jars. The jars could then be used to perform the same electrical experiments as if they had been charged by rubbing a glass in the laboratory. The sameness of the electrical matter with that of lightning had been proven.
And how did that work? All right, so a couple of questions regarding this.
Later, Frank the sparks in his experimental laboratory, and
there are two questions. So question number one, did it really do the experiment? I'm talking about flying a kite in an electrical storm. And the second question is,
the events of this fateful day are described
what would have been the purpose of it? What is it that he's
by his
trying to prove
close
to
friend and
himself?
fellow scientist.
Okay, so what's the, I mean, why would you just go out and, hey, so let's just fly a kite in an electrical storm? What is it that he's trying to prove? What's the purpose of it? All right, so the
pointed wire, which was to draw the lightning from the clouds. They were in the storm for a considerable amount of time with nothing happening. Then, just as he was about to give up, he put his knuckle to the key and felt a definite electric spark. Can you imagine his excitement? The exquisite pleasure of that moment. He transferred the charge from the key to the electric jars. The jars could then be used to perform the same electrical experiments as if they had been charged by rubbing a glass in the laboratory.
That's called lightning in a bottle. How cute. This is the experiment that made Franklin famous, at least to you guys in general, and more than likely never done this experiment. Why not? The reason is because if he did, he probably would not have survived it. Franklin was diplomat's diplomat. So the question is he the sort of person who would lie about something like that? Guys, he's a diplomat. What do you think? These guys tend to be really, really good at lying stuff, right? It's not a big deal. And the reason why we think that he'd never done the experiment, the number one reason, it's not that easy to survive something like this. Most people struck by lightning, believe it or not, they do survive, but they do survive with a lot of damage. Okay, so his description of it is, oh, it generated a spark. It would have done a lot more than a spark. Next 3 people who tried to do it the way he prescribed it or described it, they didn't survive. One guy was British, didn't survive. The second guy was French, didn't survive. The third guy was Russian, he didn't survive either. This is not the sort of stuff that you would do and then talk about it later. All right, this is an experiment that you perform, and then at the end of it, you're kind of dead. So you're not going to come back out and say, hey, this is the way it worked out. This is not a survivable sort of experiment. So they supposedly he was trying to prove himself that the sparks that he was generating in the laboratory was the same as the lightning phenomenon. Okay, so you don't really, this is not the way the experiment is done, obviously. So lightning is the same as the sparks that he was generating inside the laboratory.
Basically,
okay, so here's our understanding of
you
lightning
have
so far.
a thundercloud with a positive charge sitting in the upper region, negative charge at lower altitude in the central.
So we got the initial separation of the charges, positive on top, the negative at the bottom. We don't, initial separation is through friction among ice particles. We don't know what caused the further separation of the charges.
Of the cloud, and the separation of those 2 charges creates a potential, a voltage of several hundred million volts.
These oppositely charged regions of the cloud are highly unstable and very attracted to each other. A lightning discharge is in some ways like a gigantic version of a common static electrical shock. When these sparks occur within the cloud, they are called intra-cloud lightning. When the negative charge in one cloud flows to the positive charge in another, the result is cloud-to-cloud discharge. Sometimes the negative charge in the ground, especially in tall structures, will jump directly to the positive charge in the top of the cloud. But the deadliest discharges are cloud-to-ground strikes. The Earth has a slightly negative charge, but the powerful negative charges at the base of the storm clouds repel the negative charge, causing the ground to become positive. When the attraction between these charges becomes strong enough, there is a spark.
You have a...
Okay, Dylan. After the initial separation of the charges, the top of the clouds will become positive charged, the bottom will become negatively charged. Earth, which is initially negatively charged, through polarization will become positive charged. So negative charges at the bottom of the clouds will repel the negative charges in the ground, further into the ground, and pull the positive charges to the surface. Attract the positive charges to the surface, so the surface becomes positive charge. Look at the tree, which is initially negatively charged, will become polarized to become positive charged. So the top of the tree becomes positive charge. And the same thing is going to happen to you. Your body also becomes positive charge through polarization. All right, so the distance between the bottom of the clouds and the tall object is smaller. As a result, this becomes a main target. It becomes a better target for lightning. So next question, does lightning, okay, let's watch this. Does it originate from the ground or does it originate from the clouds? Okay, so a lot of people think that it comes from the clouds because that's the way it looks like. And some people will just say it's just the opposite.
When observed with the naked eye, lightning appears to travel from the clouds directly to the ground. But recent advances in video camera technology reveal that the anatomy of lightning is much more complex. This is the U.S. Air Force Atmospheric Research Center in Colorado Springs. Here, Dr. Jeff McCarg is using a super slow-motion camera to capture lightning. To do this, he needs split-second timing.
Oh, darn it. It's a lot like fishing. You just have to get lucky and get the lightning bolt inside your field of view.
Success is rare, but 2 years ago, McCarg hit the jackpot.
I was simply watching the lightning get closer and closer, and I kept recording it, and I didn't know what I had until I went back and reviewed it.
For the first time ever, Jeff had recorded the birth of a lightning bolt in super slow motion. When played back, it shows a flash of light dart out of a cloud and zigzag downward in roughly 50-yard segments. This first stage of lightning is called a step leader.
You can see the step leader coming down here, looking for ground, going back and forth. You can see the tortuous channel it is taking as it divides back and forth.
As this stepped leader gets close to the Earth, it has an extraordinary effect on objects on the ground. They respond to the strong electric field by growing positive streamers. These reach up anywhere between 3 and a few hundred feet above the ground, as seen in these rare photographs. Finally, when a stepped leader and a positive streamer meet, the electric charge can drain to Earth, resulting in the blinding flash of light we call lightning.
The entire field of view lights up. That's the main part of the lightning strike that your eye will catch.
The new generation of cameras has enabled scientists to record a strike that lasts just a fraction of a second and play it back over 200 times slower to analyze its detail. These super slow motion images show the stepped leader making a connection with the ground. The entire charge then drains from the cloud above, seen as a series of pulses. Using the latest camera technology, scientists are beginning to unravel the mysteries of lightning.
All right, so here's what's happening. Lightning phenomenon. Ground becomes positive charge. The bottom of the clouds are negative charge. These charges are free to move up and down. So when the negative charges start to come from the clouds, these are known as step leaders. The positive charge is going up from the ground. These are known as the streamers. Okay, so when they make contact in high concentrations, that's when the lightning is born. All right, now the details. That's an electrical discharge, which means that the positive ion, positive charge atom, is going to capture an electron. The electron is accelerating in the opposite direction of the electric field. These things are moving at extremely high speed. They've got tremendous amount of kinetic energy. So they will get captured by a positive ion. So what happens to all that energy? All that kinetic energy is going to turn into heat, light, and sound. Okay, that's a cop-out. So we need to come up with an explanation as to how heat is generated, light is generated, and the sound is generated. So what's happening is this thing is moving at extremely high speeds. When this is captured by an atom, what it does, it's got tremendous amount of kinetic energy. It tries to free itself from the atom, so it starts to jump around. All right, that's known as quantum jump. When the electron is jumping inside the atom, it emits light, so it loses energy in the form of light. So that's where you end up getting the light from. Atom is not going to be standing still. This atom is like 2,000 times larger, more massive than this one is. So what the atom does is starts to vibrate back and forth. That vibrational motion is known as heat. It's the average kinetic energy of the atoms and molecules is known as heat. That's something that we discussed last week. So this thing is going to start to vibrate back and forth because the electron is just jumping around. It's just going nuts. And so it's going to sway back and forth, slowly. When I say slowly, it's like 1 trillion times per second. This thing is moving much faster. And then the air is going to heat it up. It creates a partial vacuum. So what happens as the vacuum cools down, the air is going to just rush into it. So there's going to be collisions among the molecules. So you end up getting this sound out of it. So that's called electrical discharge. So that's for mathematical reasons. All right, so plain getting it right.
It's one of the very early strikes that we had where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in the canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the...
All right, so when there's lightning, what the lightning does is it deposits the same charges on the metal frame. All right, so when you have a metallic enclosure and when you deposit the same charges onto that metal enclosure, in essence, you're charging that metal up. So which means that the metal is going to have the same charge, like charges. Like charges will repel each other. Like charges repel. They will repel each other as far away from each other as possible. And then the furthest they could be repelled is the surface. All right, so as soon as there's a lightning phenomenon, as soon as you deposit the same like charges onto a metal surface, it's a metal enclosure, boom! All the charges will be repelled to the surface. So on the inside of the metallic enclosure, you're fine. Outside is going to be charged. Inside is not going to have any net charge. All right, so examples of metallic enclosures: airplanes, the cars, Faraday cages. All right, so the safest place to be during an electrical storm is inside a metallic enclosure. It looks like a conductor, so as soon as you put charge on it, like charge, as soon as you put net charge on it, the net charge is going to repel to the surface. You're on the inside, you're perfectly fine. You're on the inside, you're perfectly fine. Got it? You're inside an airplane, you're perfectly fine. You can touch the inside of the metal, you're fine. There's no net charge on the inside. The net charge is on the outside. The reason is because these charges will repel each other as far away from each other as possible. The furthest that they could go is the boundary. That's the outside surface. Net charge on the inside is 0. Net charge on the outside is the net charge itself, positive or negative. Whatever it is, then whatever the net charge you place on a metal, like charge will be repelled to the surface immediately.
If you can't do that, you should get into a metal car.
The car's metal body discharges the current away from the driver and to Earth.
All right, so the net charge is going to get repelled to the surface. Net charge is negative or positive, doesn't matter. Like charges will repel. The furthest that they could be repelled to is the surface, so they will be on the surface. All right, there won't be any net charge on the inside. So you can touch all the metal on the inside, you're perfectly fine. So the question becomes, but you also, the people go, Ken, but you also say you can touch the outside of the metal and you're still fine. Yeah, well, that's a discussion that we will have shortly.
True or false? You can be electrocuted by lightning in your car. The answer is true.
The answer is false. This is your commercial TV. The answer is false. It's not 50% false. It's not 70% false. It's 100% false. You would not be electrocuted by lightning in your car. Not gonna happen.
Watch. You're about to see actual video of what it would look and feel like if it happened to you.
Ah! Oh my God! The car was just struck by lightning! Oh my God!
This young man from Colorado was lucky not to be electrocuted. The outer surface of his car took the hit, blowing out his tires as the lightning sliced through his car and into the ground.
What happened was that it hit the radio antenna. It used to be right here. The antenna going up about that high.
If you find yourself driving through a lightning storm, pull over and keep your hands on your lap. Don't touch metal like the steering wheel or the radio. That way, you'll survive this.
You'll survive that because you're inside a metallic enclosure. When there's lightning that strikes, lightning deposits a net charge onto the metal surface. It's a metallic enclosure, so the light charges will repel each other. The furthest that they can repel is the surface itself. Well, there is no penetration of the charges into the metal surface, in through the metal surface. I know that because the lightning hits, engine is still working, windshield is still working, so the electrical system is fine. What else do we know? I don't know. I see the clock, electronics is fine, so there was no penetration in there. This guy is yelling and screaming. He didn't get touched by lightning. It was more of a psychological state of shock. That's the reason why he's just, oh my God. That's the reason why you hear the poetry that you were hearing. And he's fine. So what happened to lightning? The tires, did that help? Nope. Lightning just went right through the tires into the ground. So that's perfectly fine. So what attracted the lightning evidently was the antenna, which got completely vaporized. And then based upon the erroneous conclusion,
going up about that high.
If you find yourself driving,
now that they just messed up the physics completely, now they're going to give you some amazing commonsensical conclusions and suggestions based upon those.
Through a lightning storm, pull over and keep your hands on your lap.
Because if you were to do that, if you were to stop on the road, and because of if the traffic comes to a stop, if I'm anywhere near you, I'll come after you with a baseball bat. All right, keep on driving. Don't stop. You're just about to be in the safest place where you could be in a lightning storm. One thing that you need to do is just roll up the windows. Roll up the windows. And there's a reason for it. And you will find
Don't touch metal like the steering wheel.
You can touch all the metal you want on the inside. You're perfectly fine. This guy was touching the metal. He was already driving. He kept driving through a lightning strike. One of my students ended up missing class. This is like 10 years ago or something. And this guy was really good. He was in his 30s. He's one of the mature students who would never, under any circumstances, he would never miss a class. He said, Ken, I had a perfect excuse. He said, something happened to me. I just want to share it with you. Evidently, he was on a run, come to school that morning. And then everything just went white. That's it. And then the engine was running, and the car was having a hard time driving. He didn't know what happened. There was a complete whiteout, just briefly for a fraction of a second, and then boom, engine is struggling, and the car was not. It was moving barely. And then somebody pulls up next to him and say, "Dude, you just got struck by lightning." He had 4 flat tires. That's what happened. And good thing he's taking some pictures of it. So he did a 5-minute presentation. That's 5 actual credit percentage points for the experience of it. They say he didn't even notice that he got struck by lightning.
The monster created by a man they called Mad is turned loose to strike terror into the hearts of men.
Austin Richards is a self-described mad scientist. But tonight, He's going to play both Dr. Frankenstein and the monster at the same time. He plans to zap himself with 2 million volts of electricity, protected only by a homemade metal suit.
I've really been obsessed with the idea of being a mad scientist. The mad scientist knows exactly what he's doing, but at the same time there's sort of an element of unpredictability to what he's doing. Sometimes it gets out of hand.
Austin's interest in current events began when he was 14 years old. For a Halloween show, he built what's known as a Tesla coil, a machine that shoots fiery bolts of electricity through the air.
And that first Tesla coil made sparks that were about 12 inches long.
Tonight, Austin is unveiling his latest creation, 2 giant Tesla coils that can fire 2 million volts over 20 feet. But he isn't satisfied with just watching this dangerous light show. He wants to be part of it. Austin knows he could never survive a direct hit from the giant coils without some sort of protection. So he designed a special suit made of metal that would transform him into a human lightning rod. The idea for the suit first came to him at a restaurant, and he quickly scribbled his original design on a napkin. Eager to bring his creation to life, he went shopping for parts at the local hardware store.
So I started selecting bits and pieces of heating duct and dryer duct, actually trying them on my body, slipping them on my arms and legs, and I got some interesting comments from some of the people that work there.
That makeshift suit has now evolved into this, makeshift suit. And though he may not make any best-dressed lists, Austin hopes his suit will protect him from a 2 million volt direct hit.
What we're going to try is something that's never been tried before, which is to create almost, in a sense, double jeopardy, having 2 Tesla coils, suffusing a whole area with electricity, and I'm going to put myself right in the middle of it.
Austin has invited a select group of guests to witness his terrifying experiment. But are they going to see an electrifying performance or an electrocution? Austin begins by displaying the awesome power of the giant Tesla coils. He holds up a block of wood. It bursts into flames, but he's shielded by his protective glove. So far, so good. Next, Austin ups the stakes by raising up a solid steel wrench. It's bombarded by a barrage of bolts, but he's still okay. Now he's going to step right into this electrical storm and subject himself to 2 million volts of white-hot lightning. This scientist must be mad. If Austin's homemade suit should fail, he could be fried to a crisp.
If I haven't done my safety check properly, I could die.
He cautiously moves into position. The coils surge to life. Millions of volts of raw power pound his body. The shocked onlookers can't believe what they're seeing. It only takes 100 volts to kill someone. So how could Austin survive 2 million? Incredibly, he's done it. Austin's electrifying experiment is a success.
I was really hoping that it was going to work, in the sense that I was really hoping I wasn't going to get killed or injured. And I remember feeling a really deep sense of relief when the arcs began hitting and I didn't feel a thing.
Beaming with success, Austin lights a cigar to celebrate. His crazy homemade suit actually works. Maybe this mad scientist isn't so mad after all.
It's alive! It's alive!
This guy made it look real easy. He's in a metallic enclosure. He knew that he was going to be perfectly safe. He's also a physicist. He understands the physics of it, as well as I do, if not better. One of the things that I want you to notice is, if you knew that you were about to be struck by lightning, and if you were to jump, would that prevent you from getting struck? I think you got your answer, right? You don't need to be grounded. If you were to jump, that's not going to happen. All right, so you still get struck. It was still part of the current going through his body. The only reason why he's safe, because the net charge remains outside of the metallic enclosure. So this is known as a Faraday cage. The examples of Faraday cages in a metallic enclosure, a car, airplane. And anything else that houses electronics within, which is like, I don't know, your computer, for example. All right, so if you want to protect any sort of electronics, any sensitive electronics from outside influences, you always put them inside a metallic enclosure.
When a thunderstorm forms, people's lives can be at risk.
We tell people when thunder roars, go indoors. What we mean is seek a safer shelter.
If you're ever caught out in a thunderstorm, one of the safest places to be is in a closed vehicle.
Many people believe the rubber tires on a car will keep them safe, but that's not true. It's the car's metal body that provides protection, as this high-voltage experiment will demonstrate. A Tesla coil is the lightning simulator. An electrical transformer that discharges 3/4 of a million volts of electricity, more than enough to kill. Dr. Lisa Lazarek is an electrical engineer who's willing to sit in a car underneath the coil to prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car. But it's one thing to talk about the theory, and it's another thing to put it into practice. So I guess I'm ready.
The electrical charge flows around the metal body of the car and discharges harmlessly to the ground.
I'm fine. The theory has worked as expected. My feet are slightly tingling, and because I was nervous, my hands are still clamped together. But other than that, I'm fine.
Okay, so what you guys see wrong in this video?
When a thunderstorm forms,
You guys see
people's
anything
lives
wrong
can be
in
at
this
risk.
video?
We tell people when thunder.
This is one of the things that I want you to notice is the progression of commercial TV. Okay, so this is from, she said, Gustavo, give yourself tampons. Okay, so she's afraid to touch the metal on the inside, despite the fact that it's perfectly safe. And coming from her, that's surprising because she already has a PhD in electrical engineering. Okay, that's engineering is applied physics. I would think that she would know that that's perfectly safe, but evidently she doesn't. And the sad part of it is Discovery Channel picks her as their expert, which is kind of sad as well. And a lot of people think this person is a PhD and she should know her stuff. And you're thinking, oh, so I shouldn't be touching the metal on the inside either. You can touch on the metal on the inside. Okay, so the TV, especially the commercial TV, is not a good source of science knowledge.